The engineering group promotes engineering geology and supports technical advancement through the production of engineering group special publications. These mostly arise from a working party of experts, and tonight you'll hear from the Groundwater Working Party about the EGSP that is nearing completion.
Okay, thanks very much, Ursula. So yeah, tonight I'm delighted to be able to launch the latest in the series of engineering geology special publications. The theme and title of the report is Engineering Geology of Groundwater in Design and Construction. And as Ursula said, my name is Ian Duncan. I'm the chair of the Working Party and the lead editor of the special publication. And I'm going to provide a brief introduction to the report before some selected authors provide more detail on the content of each key section, and then we'll follow with some questions. Again, can you all mute? Can you turn your cameras off except for the person who's speaking, which should only be me, please? And if you wish to raise questions, please type in the chat box or use the hands up, and all the questions will be dealt with at the end. Next slide, please, Ursula. So water is every civil engineer's greatest enemy. I'm sure we can all relate to this comment and ignore it at our peril. So here are two examples of groundwater management, one of which has gone very wrong. The figure on the left there depicts the Cologne City Archive collapse, which happened in 2009. A tunnel crossover was under construction below the archive within sands and gravel deposits. The groundwater cutoff design comprised diaphragm wall and grouted ground block with external dewatering. The grouting was insufficient, and combined with the dewatering caused high pressure inflows of groundwater into the subsurface excavation, bringing with it a significant amount of material, eventually causing a void and rapid collapse of the building above, which unfortunately resulted in 2 deaths. The figure on the right, however, shows a well-executed groundwater management system for a wastewater treatment work in Kent. Next slide, please, Ursula. Quick history of the special publication. We had a steering group formed from the people listed in the membership there in 2015. And we've been working hard over the last 5 years, developing the content leading up to the book launch today and publication next year. Next slide, please. One of the key requirements of the special publication was the use of geological models to drive the direction of the report. It was recognised that within ground engineering, modelling terminology is not necessarily aligned, particularly between hydrogeologists and engineering geologists. So with the special publication, we wanted to make sure that we reach a common understanding and usage of modelling terms. So the IAG Commission C25, Engineering Geological Models, introduces 3 models that are used and developed through the various stages of project development to identify uncertainty and manage risk. Those are the conceptual, the observational, and the analytical models. And it is these models that have been adopted and widely referenced in this special publication and will be discussed in more detail later in the presentation. Next slide, please. So what have we achieved with this publication? It gives a state-of-the-art review of engineering geological considerations for managing the risks associated with groundwater during design and construction. The book provides the basis for engineering assessments through development of conceptual, observational, and analytical models to support those working with groundwater. It's a publication that will act as an essential reference handbook for professionals, as well as a valuable textbook for students and others. The style is concise and digestible by the non-specialist, yet authoritative and up-to-date, and extensively supported by data and illustrations. So the content embraces a full range of topics and latest research findings to practical applications of existing information. The book provides worldwide experience of the subject matter and draws upon the in-depth knowledge of the Working Party members and other publications on engineering geology of groundwater. Next slide, please. And here is our esteemed team that have been working on this so hard over the last 5 to 6 years. I'm not going to read you all out, but thank you to you all in your respective organisations. Next slide, please. So the scope of our report. This publication provides guidance for the managing of groundwater during design and construction of engineering projects. The publication uses ground models to illustrate geological and groundwater concepts and how these can be presented as project hazards and subsequently quantified as risk. The chapters provide the reader with a fundamental knowledge and tools to develop a conceptual model, refine this with observation data to create an observational model, and finally test the model. Problems associated with groundwater are highlighted and methods to control groundwater are discussed, together with examples how groundwater can be successfully managed in surface and subsurface applications. Case studies are referenced throughout and collated in the final chapter. Next slide, please. So, typical engineering applications included in the report are the groundwater impacts on, e.g., tunnels or landslides. And the area of interest is that area which is less than 100 metres below ground surface. And for the purpose of this publication, all water in the ground that's below the surface is considered as groundwater. Related topics listed below are mentioned, but not in significant detail. Water resource management extraction, deep groundwater issues, reservoir engineering, geothermal, and groundwater transport of contamination. Next slide, please. The structure of the book is broken down into three principal sections: the introductory chapters, modelling of groundwater, and application and management. Authors Tim Blower, Mark Lee, Martin Preen will now take us through these sections, describing the content and the chapters included. Then William Powery will then present one of the key case studies from the special publication. Next slide, please. Over to you, Tim Blower, for the next section.
Thank you, Ian. Can I just have a thumbs up that you can hear me? Somebody will give me a thumbs up. I trust you can hear me. Yes, there we are. Thank you very much. So after a short introduction section, the early chapters of the publication cover the theory of groundwater flow, problems caused by groundwater, and a framework for groundwater risk management. Next slide, please. But before we dive into those various sections, I thought it'd be useful just to start with a quotation or a series of mini quotations, with apologies to Margaret Atwood. Water does not resist, water flows. Water is not a solid wall, but water always goes where it wants to go, and nothing in the end can stand against it. If you can't go through an obstacle, go around it. Water does. And it's this propensity of water to sort of go where it wants to go and do what it wants to do, which is key to many of the problems that we have in geotechnical engineering as a result of groundwater. Next slide, please. So one of our starting points was to record some of the problems that we as ground engineers face as a result of the effects of groundwater. Problems caused by groundwater come in all shapes and sizes, from localized seepages to regional scale problems. And we found that they nevertheless related to a relatively small number of fundamental effects of groundwater. And these are the effects of groundwater flow, including its ability to carry soil particles, the effects of groundwater pressure or pore water pressure, that's positive and negative, and the chemical properties of water, specifically its ability to dissolve and convey chemicals. Excuse me. There are some other properties of groundwater, thermal and electrical, but in the literature, these do not seem to cause a large number of problems in geotechnical engineering. And so our examples tend to fit into those three categories. Next slide, please. And we found it necessary to draw some boundaries around the problems that we're going to address, since many aspects of engineering in the ground involve water, but not all of that water is groundwater. So the book does not address the effects of surface water in terms of flows, erosion, flooding, waves, and so on, as you'd expect. Retained water is also surface water, but to the extent that that water in reservoirs and rivers, lakes and ponds can infiltrate into the ground and become groundwater, then it is included. So we don't major on dams and reservoirs, but some examples are included where they're relevant and helpful. Leaked water, again, to the extent that it infiltrates and becomes groundwater, is included. Another question is whether or not a problem is a result of the groundwater or a problematic soil. So, for example, abstracting water from a deep layer of peat would cause settlement. Now, is that a groundwater problem or is that a soil problem? Well, to the extent that groundwater contributes to the problem or is a key component of the mechanism, then we have included it in the publication. The picture in the center at the bottom shows the Holm Fen posts, which have recorded some 3.5 meters of settlement over 150 years in a peat fen just south of Peterborough, as an example. Next slide, please. So turning to problems caused by groundwater flow. These are many and varied. Apart from the obvious problems of water ingress into excavations, problems can arise from water egress from the ground, flooding due to groundwater, internal erosion effects, and groundwater diversion effects, as illustrated here. The image on the right is taken from a dam in Zambia. During construction in the mid-1970s, it was noted that new springs of hot water appeared in the river channel downstream of the dam. This led to concern about the stability of the dam, and additional measures had to be put in place, including these relief wells and a stabilising berm. Once installed, the dam was completed without incident. It was later discovered that the construction had blocked natural groundwater flow pathways that emerged in the riverbed at the dam site. The groundwater flow thus had to find an alternative outlet. However, with these wells installed, the dam has been stable now for 50 years and the wells continue to flow with warm water to this day. Next slide, please. On the subject of obstructing natural groundwater flow paths, we should also acknowledge the event that played a very significant part in the starting off of the whole field of engineering geology in the UK, and that was the Abervan disaster. On the 21st of October 1966, over 100,000 cubic meters of liquefied colliery spoil slid some 600 meters from a hillside tip, crossed a canal and a railway line, and spilled into the village of Abervan. The slip destroyed 18 houses, a junior school, and part of the neighbouring secondary school. In total, 144 lives were lost, 116 of them children. For those not familiar with these events, I urge you to read the tribunal report from 1967. It concluded that water had contributed to the disaster in four separate ways, all of them connected with groundwater. It's also very poignant to note that in an appendix to the report is the sketch shown on the slide. Quite clearly, it's an early conceptual model used to communicate the risk of obstructing natural springs to the tribunal authorities. If such a model had been developed before the tip's construction, the disaster might very well have been avoided. Next slide, please. Problems caused by groundwater pressures. Well, these problems are so numerous as it's possible to list them all, but I've listed a few examples on the left here. And just to pick up one typical type of example, the photograph on the right shows us the Rothbury landslip in Northumberland a few years ago. The failure mechanism was related to increased pore water pressures and reduced effective stress following heavy rainfall. Despite small movements over the preceding years, nothing very much was done to address the problem, except resurfacing the road to cover over the cracks. That was until the major slides happened. Next slide, please. Underground works have their own particular vulnerabilities to groundwater problems. Aside from the obvious problem of excessive groundwater ingress or egress, tunnel face instability can be caused by groundwater. Invert heave and various forms of lining failure can occur, and groundwater can contribute to the problems of ground swelling. Taking the image on the bottom left, sections of the invert slab in the tail race tunnel of a hydropower development in Uganda had to be replaced due to groundwater uplift failure during construction. The tunnel had been designed to leak, meaning that water ingress would be expected and water pressures would be relieved. However, the contractor, following their normal practice, had installed water bars across the joints in the lining, The result was that the water pressure built up and the temporary invert slab, which hadn't been designed to resist these pressures, blew, causing delay whilst remedial works were implemented. Next slide, please. And the first image, please. I expect many of us, if you just click the first image across, please. Thank you. Yes, I dare say many of us can remember driving around the north side of the M25 about 10 years ago and seeing the spotty chalk slopes. These were an extraordinary lesson in engineering geology just to look at them. Of course, the problems caused by dissolution in carbonate rocks are very significant, also very widespread across the UK, and amount to a whole subject area in their own right. So in the book, we refer to the dissolution of carbonate and other types of rocks, and acknowledge the contribution over many years of authors such as Tony Waltham, Clive Edmonds, and others on this subject. Just click the next image, please. Some of you may remember the shocking failure of the Carson Dam in 1984 as it neared completion. However, perhaps fewer will remember the tragedy that unfolded the previous year during the dam's early construction. Acidic runoff from the dam's mudstone fill reacted with crushed limestone that had been used in the drainage layers. The result was carbon dioxide, which accumulated in tow drains, manholes, and other excavations, and led to the deaths of 4 workmen in a manhole in 1983. So an example of chemical reactions and the transportation of gases. Next slide, please. Of course, without some principles and a technical framework to guide us, these groundwater problems are just a series of engaging, if sometimes tragic, anecdotes. So we need a level of understanding, even a language, to describe the problems, to help us work our way towards finding solutions and finding means to model and analyse them. And that is why we include at the very start of the book, chapter 2, in which Professor Tellam and Dr. De Freitas set out key principles and concepts of the theory of groundwater flow. The document should be equally useful for those needing a background from scratch and for those who have some experience but using the book as a reference point. It uses a narrative text supported by figures and with boxes to help explain more advanced aspects. It was written collaboratively by a hydrogeologist and an engineering geologist, so it's couched in engineering terminology and examples rather than in water supply ones. It's figure heavy and maths light. It can be understood by readers with a limited memory of their college maths, but nevertheless includes enough to provide the background needed to make the most out of the wide range of groundwater problems and their solutions that are covered in the rest of the document, and to enable many useful calculations to be undertaken. In terms of coverage, it gradually builds up from the meaning of Head and Darcy's law and their use in steady state systems, and it discusses hydraulic conductivity, including anisotropy and fracture flow, and then moves on to unsteady state flow. It further extends flow theory to the unsaturated zone and also examines causes of water level fluctuation. And finally, it also deals with the basic ideas of solute transport in heterogeneous media. Next slide, please. So now we're armed with a vocabulary and some understanding of the theory of groundwater flow, so we can start to analyse the problems that we come across in our day-to-day working lives. But moving forward towards solutions, we need a framework to help us manage groundwater risk. So chapter 4 is a brief chapter that sets out how we've adapted the concept of these various engineering geological models to provide a framework to help us manage groundwater risk. The concept of engineering geological models in this context come from the IAEG C25 report by Steve Parry and others, who identified these 3 types of models: the conceptual engineering geological model, the observational engineering geological model or ground model, and the analytical model. I won't dwell on these now because Mark Lee will take over in a minute and describe these in more detail, but I'll just say that Chapter 4 addresses such matters as using these models to identify hazards and the concepts of risk ownership and risk communication. So I'll stop there now, thank you, and hand over to Mark Lee.
Thanks, Tim. Can I nick your trick and just see if I can get a thumbs up that people can see and hear me okay? Fabulous, thank you very much. So yeah, as has been discussed, the IAG C25 was established to present the philosophy behind the development and use of models in engineering geology. And the Working Party have very much sought to align our approach with that established in C25 and use the framework identified as a basis for practitioners in developing the different types of model. Next slide, please. So the key consideration when using models is to remember that they're tools to help better understand a specific site setting, including its hydrogeology and how that interacts and influences engineering activity. It's also important to remember that the use of models is an iterative process with a conceptual model underpinning and being refined by observational models and appropriate analytical models. And this is a slightly modified version of the C25 model development process, showing an additional step that may be necessary, effectively to revisit and refine the conceptual model following the development of an analytical model. Next slide, please. So geology, as I'm sure we're all aware, informs the potential for ground-related problems at all stages of projects. By all stages, I mean from site or route selection through outline design, detailed design, construction and operation of an engineering project or scheme. Geological information is routinely appraised to inform the engineering decision-making, but hydrogeology is not always appropriately considered. And this publication aims to address some of the commonly overlooked or misrepresented aspects of site conceptualization, specifically in relation to groundwater. The geology naturally controls the hydrogeology. How strata were formed and have changed over time, formation of structural controls such as faulting, or changes in inherent material properties through natural geological processes, all influence the behaviour of groundwater. And a suitable hydrogeological conceptualization is a key to understanding the response of the ground and groundwater to engineering activity. Next slide, please. All of the failure mechanisms that occur can relate to a poorly conceptualized understanding of the hydrogeological setting. And when considering carrying out engineering activity, one should adequately understand the context in which the work is planned. Many engineering failures, such as Abervan and Carson Dam that have been discussed today, were a direct consequence of poor conceptual understanding of the ground response to groundwater conditions altered by engineering activity. On the right, there are some figures showing groundwater-induced mechanisms for instability in excavations, resulting from improperly controlled groundwater. These are situations that can and do arise today, which are avoidable with appropriate conceptualization of groundwater in an engineering context. While it's possible to control groundwater, or indeed not encounter problems without having developed the correct conceptual model, it's not an approach to be recommended. You can get lucky, but luck only gets you so far, and it's much better to manage ground risk by appropriate conceptualization. Next slide, please. Once you've established your conceptual model, it's important to be able to effectively communicate that understanding to others. Now, this clearly includes the geology, hydrogeology and engineering components, but you may also need to consider other factors. It's necessary to take into account changes over time, perhaps. Groundwater conditions may change seasonally. There's also the scale of interest. It's important to understand the lateral and vertical extent over which the hydrogeology should be considered. This usually goes some way beyond the immediate limits of the engineering works. And conceptual models have historically been communicated in a report format, setting out data sources, interpretation, and visually with schematics as shown on the right. This is pre and post construction steady state conditions. Nowadays, there are also emerging digital tools which can aid visual communication and allow others to interrogate the conceptual model in 3D and more easily show changes to non-steady state conditions. I think it's important that we as practitioners take advantage of these evolving tools to better communicate with each other. Next slide, please. Once you've developed an initial conceptual model, you may have identified data gaps, or there may still be an unacceptable level of uncertainty in the characterization of the hydrogeology. This is where the observational model comes in, An observational model being a conceptual framework with quantitative elements for the behaviour of the ground and groundwater system. And it's built up by observations from a variety of sources, such as those shown on the slide. And the observational model confirms or updates the understanding developed in the conceptual model, and it also addresses uncertainty that can't be resolved from existing data sources. This is effectively where new data is collected to update understanding. Next slide, please. I think we jumped one there. That's strange. I'm missing. One's missing. They jumped out of order. Oh well.
Let me see if I can find it, Mark. It
Okay,
might
no
be
worries.
it might be
somewhere.
hidden. Yeah, it is.
Someone shuffled the deck.
No, it's hidden.
Okay.
There we go.
I hope it's been worth the wait.
There we go.
Perfect, thank you. So, to address the uncertainty in your conceptual model, or indeed demonstrate that the anticipated conditions are representative, a hydrogeological investigation is required. It's important that the design of a hydrogeological investigation is appropriately considered and suitably scoped to maximise value. And investigations need to use appropriate techniques and methodologies and be targeted to test the understanding or address a specific gap in the conceptual model. And it's really important that both space and time are considered when looking at the hydrogeology. The next slide, please. So, for example, the design of monitoring points is really important as this influences the data that's collected, which may represent different aspects of the hydrogeology. Long standpipes with long screens, shown on the diagram as A, will record average water levels across multiple strata, whereas short screen standpipes, shown as B, or piezometers, shown as C, can be used to target discrete horizons, as can vibrating wire transducers, either installed in sand stills, as shown in D, to provide a direct hydraulic connection with a specific strata, or grouted in a borehole with multiple monitoring horizons, as shown in E. It's also possible to incorporate long-term monitoring into engineered structures to provide real-time data for hydrogeological conditions, shown on F. All of these are monitoring points that record level or pressure of groundwater, but the data collected by each is only appropriate to answer specific questions. And it's important to understand what those questions are and how they advance the conceptual model when using observational models. Next slide, please. Now, analytical models come in many forms, comprising both analog and mathematical models that describe or represent a process, system, or concept by means of variables and governing equations. When we're describing mathematical models, no distinction is drawn between closed form or more complex iterative mathematical models. And it's the mathematical models that practitioners most commonly think of when discussing analytical models. And this is one of the common challenges in sort of integrating the different specialisms in engineering geology of groundwater, is the use of language. One person's analytical model is another's numerical model. Now, this publication aims to overcome this barrier by providing a common vocabulary to facilitate clearer communication. It's not a step-by-step guide to all of the analytical models available, but rather a guide to what should be considered when selecting and using an analytical model. Next slide, please. Perhaps more than the other types of model described in the publication, analytical models are open to misuse or misrepresentation when trying to understand the engineering geology of groundwater. They're based on a series of underlying assumptions which must be met for the answer they produce to be meaningful, and the right model must be used. It's no good using a model that solves for flows if the problem under consideration relates to pore water pressure. Models have many non-unique solutions, which is to say that they can produce the same answer with different inputs, and it's up to us as practitioners to ensure the models are representative of the conceptual and observational models that underpin them. Analytical models may be mathematically correct, but geologically incoherent. Analytical models are limited by their underlying assumptions, but also the data that constrain inputs and reduce uncertainty. How the analytical model refines and confirms the conceptual model is the key point. If there's a discrepancy, is it in the analytical model, or does the conceptual understanding need to be updated? It may be that further data needs to be collected using additional hydrogeological investigations to answer this question. It's part of the code of conduct that we all sign up to as chartered geologists to know the limits of our professional knowledge. The purpose of this publication is not to provide training in how to become an expert, but to facilitate the meaningful discussion between specialists. Next slide, please. The publication sets out what to consider when using analytical models, how to avoid common pitfalls, and how to effectively communicate the results, including any residual uncertainty. It also addresses whether there's a need for an analytical model in the first place. It may be more effective to simply increase a factor of safety slightly than undertake analytical modelling. It also considers how complex the analytical model needs to be. There's often a rush to use software, but actually hand calculations with closed form solutions are equally valid and maybe quicker to complete. The amount of data available should also be considered when trying to constrain uncertainty, both in defining inputs and validating outputs of analytical models. And the consideration of how far you need to reduce uncertainty to establish an engineering solution. Analytical models, as well as conceptual models and observational models, can be incredibly powerful tools, but they must be used appropriately and with due care to understand their limitations in the context of furthering the conceptual understanding. This publication aims to aid practitioners in undertaking best practice by providing accessible and practical guidance around the use of models. And I'll now hand over to Martin Preen to talk through what you can do once you've established a robust understanding of the engineering geology of groundwater through the use of the different types of model.
Next slide, please. Thank you, Mark, and good evening, everyone. So perhaps can I ask for a few suitable emojis to confirm people can hear me? Thank you, a good selection of emojis there. So I'm now going to talk to you about the next section of the book, which builds on the principles described earlier and talks about how groundwater can be applied, or ground control can be applied, and how groundwater can be managed with a specific focus on construction projects, because that's the scope of our book. Chapter 8 deals with ground control methods. Chapter 9 is called Managing Groundwater in Practice, and chapters 10 and 11 respectively deal with groundwater management applications for surface excavations and for subsurface excavations. Subsurface excavations effectively relating to tunnels and shafts and so on. Next slide, please. So the first chapter in this section is groundwater control methods and basically gives a brief overview of the available methods. It covers groundwater pumping methods, both those that actively pump and those that rely on passive drainage. It covers groundwater exclusion methods, including those where we install a physical wall in the ground, perhaps sheet piles or diaphragm walls, and those where we try and change the properties of the ground by grouting or ground freezing to reduce the permeability. It also deals with those methods that apply a fluid counter pressure to keep the groundwater out, obvious examples being compressed air tunneling and close-face tunnel boring machines like EPB machines and slurry machines. And essentially this chapter provides a toolkit of the available methods, and it highlights that the designers, be they engineers or geologists, it's not sufficient for the designers to understand the geology. You need to understand the methods that are going to be applied, because these methods are not interchangeable and only work in certain conditions. Next slide, please. This chapter is called Managing Groundwater in Practice, and we're here tonight talking about a book that's been published by the Geological Society. I think this chapter might set a record for the least amount of geology in it in any book chapter, because essentially it's a chapter about the process of managing groundwater. It involves identifying the objectives. It involves knowing that many activities related to groundwater, particularly those in construction, such as construction dewatering, are effectively regulated. So many of you will know that, for example, in the UK, in all parts of the UK, you need to obtain permissions to carry out various forms of groundwater dewatering. And the regulators are, for example, in Scotland, it would be SEPA or Natural Resource Wales in Wales and so on. This chapter also discusses how groundwater control and instability might be influenced by health and safety in design, and how health and safety might influence the ground control. There's the discussion of groundwater guidance documents, codes and industry standards. Obviously, the chapter and the whole book has a UK focus, but we do discuss international examples as well. It's also important to realise that groundwater management schemes have a time scale. There's an implementation or an installation period, but then there may be an operation period where pumping is carried out. There might be a need for monitoring, and like many engineering elements, at the end of the groundwater control process, there's a need for decommissioning, and this chapter addresses all those aspects. Next slide, please. So this chapter deals with the application of groundwater management for surface excavations. And by surface excavations, we mean relatively conventional excavations, basements and so on, buried tanks, pipelines. But as Tim highlighted in his discussion of the earlier chapters, there are quite a wide and diverse range of groundwater problems, and we try and cover those. That includes groundwater management for slopes, embankments and earthworks, filters and erosion management, and also dealing with groundwater problems in water retaining structures such as dams, how groundwater interacts with ground improvement, and also we address instrumentation and monitoring. The picture on this slide is an example of one of the more unusual problems. Thank you. Where it's a British library at Euston in London, and this is founded on deep piles in the sands of the Lambeth Group. And below the Lambeth Group, there's the chalk, which is known as the Lower Aquifer in London. Many of you will know that the water levels in the chalk are now artificially lowered as a result of historic 20th century pumping. And there was a concern at the time of building this building that the water levels would rise, and that would change the pore water pressure in the Lambeth sand, which is something like 30 or 40 meters below ground level. That would change the effective stress, and it would therefore change the bearing capacity of the piles. So you get the slightly unusual or perhaps not very obvious scenario that a change in groundwater level in an aquifer 40 meters below the site could affect the structural movement and condition of a near surface building. It shows one of these slightly unusual groundwater problems. Next slide, please. So this chapter deals with subsurface excavations, which we broadly mean as tunnels and shafts. We discuss how groundwater problems can actually influence the appropriate form of construction of a shaft, whether you have a pre-lined shaft where maybe there's a sheet pile wall or a secant pile wall, or whether you can sink the shaft as a caisson, or whether you can use excavation support where maybe you're excavating and supporting the face with spread concrete linings. There's a discussion of tunnel construction related to groundwater, both open face and closed face tunneling machines. And there's also the measures we can effectively carry out from within the tunnel, so-called in-tunnel measures, where we can drill out and construct groundwater depressurization wells, or we can drill ground treatment holes to try and freeze or maybe grout the ground. And then the final part of this chapter is to do with tunnel maintenance in relation to groundwater ingress and also instrumentation and monitoring. So that's the end of the section on applications. I'm now going to hand over to William Powery, who will be talking about case studies.
Thanks, Martin. So if we could move on to the next slide, please. So good evening, everybody. This is the list of case studies in the report, and I'm not going to read through them, but what we've tried to do is to give a selection of case studies which are of interest, illustrate many of the techniques which are covered in the book as a whole, including the whole process of conceptual, observational, analytical modelling, and also the effects of groundwater and groundwater control in practice. So I'm going to talk in particular about just one of those case studies tonight, and that's the A55 North Wales Coast Road Conway Crossing. And that illustrates a number of different techniques of groundwater control relevant to the particular ground model that we had at the site. And there's also a little thing at the end which didn't go quite according to plan. So if we can have the next slide, please. So the picture when it fades in, this is a view of the Conway crossing taken during construction. So we're looking inland into the Conway estuary, and those of you with sharp eyes, unfortunately I can't use my pointer, but those of you with sharp eyes can probably see Telford's Bridge, which is near the top of the picture. That's it. Brilliant. Thanks, Ursula. Okay, so there's Telford's Bridge and the causeway. And then what we can see, the yellow dotted thing, is the line of the tunnel. So it was an immersed tube tunnel. It was decided to be a tunnel rather than a bridge for environmental reasons. And there are 3 excavations in that picture. So the one on the sort of top left, at the left-hand end of the yellow dotted line, is the eastern cut and cover approach. So that's the tunnel approach which was constructed in a cut and cover. At the other end is the western approach. And then the 3rd excavation is the casting basin. And that's where the tunnel units themselves were made. So these were basically reinforced concrete sections, about 120 meters long. They were built in situ, and then eventually the casting basin was breached and they were floated out into position and lowered into position on the Conway estuary and joined up with some clever joints to the cut and cover sections at each end. So all of those 3 excavations are actually on reclaimed land. So the total depth is between 10 and 15 meters below mean high tide level, and they're protected from the estuary by a total of about 2.5 kilometers of bunds and embankments. And there are different natural strata there, all of which required groundwater control. So if we can move to the next slide. Okay, so this slide, when it eventually fades in, shows a schematic cross-section through the bund protecting the casting basin from the Conway estuary. So the bund itself was made of alluvial sand and gravel, so that was quite high permeability. So the principal means of control of seepage in from the estuary was a grout curtain of vibrating. It was installed by means of a vibrating H-pile, so it was a thin grout cutoff. And because at the time we weren't quite sure how well that would work, there were two stages of well points, which again you can see in the diagram. The two stages were necessary because the drawdown was well in excess of 6 or 7 meters, which is the limit for well point dewatering. So they were installed to mop up any residual seepage. Below the alluvial sand and gravel, there was a layer of Irish sea boulder clay. That was as tough as old boots, and that was going to remain undrained for the duration of the construction. So we didn't need to carry out any pore water pressure control measures in that. The one below that, which is shown laminated, is the Glacial Lake deposits. And that had got a horizontal permeability of about 4 times 10 to the minus 7 meters per second. The vertical permeability was 2 to 3 orders of magnitude lower. So the problem with this stratum is that water would not readily flow out of it, so it wasn't amenable to conventional dewatering. But on the other hand, had it been left to its own devices for this sort of 18 months, 2-year construction period, the pore water pressures would gradually have re-established and cause potential instability at the toe of the excavation. Then below that, there was the bedrock, which you can just see in the bottom left of the picture. And we'd all thought that the bedrock would be impermeable. But in fact, where it was shallow, it was actually quite fractured and quite permeable. And that gave us 1 or 2 interesting issues, but actually nothing that the system as designed couldn't cope with. So if we move to the next slide. So this is a couple of boreholes through the laminated glacial lake deposits. So basically, the thicker strata are almost a clay, and they're probably about 10 millimeters, 15 millimeters thick. And then there's almost really just a dusting of a fine sand, and it's those horizontal laminations which gives it its horizontal permeability. So the dewatering or the pore pressure control solution here was these ejector wells. Basically, that is a nozzle and venturi device. They're sometimes called ejectors, sometimes called water jet pumps. And the great thing about the ejector is that it creates a vacuum in the well, and it will also quite happily pump air as well as water. So if the top of the well is sealed and it runs out of water, it just pumps air out, and the vacuum can actually help persuade water to flow out of this rather tight soil, which does need depressurization. A couple of things to note in passing are the extreme distortion in this so-called undisturbed sampling tube, especially where there is a stone in the material, which is the case about the middle of the left-hand split. And then near the bottom, we run out of the laminated structure, and it becomes much more amorphous. So this was the one that had to be controlled with the ejector wells, and they applied a vacuum to assist with the removal of groundwater and the control of pore water pressures in this stratum. Next slide, please. So this is just a view of the bund protecting the casting basin, and you can see there fairly clearly the lines of well points and the ejector line. And if we move to the next slide, we're now just zooming in, and you can see there the tunnel units being cast. So there are 6 of those being cast in the casting basin, and again, over on the right and running around the excavation, you can see the ejector lines and the well point lines. Next slide, please. This is the casting basin, again, another general view with the tunnel units nearing completion. So I think we're looking over to Duncan here, which is on the eastern side of the estuary. Next slide, please. And this is the casting basin has been breached and flooded, and the tunnel units, the ends of them have been sealed off, so they're being towed out one by one to be sunk into place on the Conway estuary and joined up. Next slide, please. So this was the West Cut and Cover prior to the start of the work. So it was basically marshland, tidal mudflats. So that's why we needed to have the bund to contain it off. Next slide, please. This is the west cut and cover during excavation. So we're looking down into the mouth of the tunnel, so out across the estuary. And the west cut and cover was the one place where we had a bit of excitement during the construction. So if we can have the next slide, please. So everything was going just about okay. We knew that the pore water pressures in the glacial lake deposits were just about low enough. And then for some reason, it was decided that another ½ metre or possibly only ¼ metre of ground would be taken off. And that led to just a little tiny spring in the base of the excavation, which over the course of about 24 hours became an absolute flood. And in the end, after initially trying to keep the excavation dry, it was decided the best course of action was to allow the excavation to flood in a controlled way and go away and think about the problem. Eventually, a series of wells were sunk, and after a number of attempts, the source of the water was reached. So if we can move to the next slide. And it turned out that just at this one particular location, whether it was an old buried river channel or something like that, there was a very highly permeable layer between the Irish Sea boulder clay and the glacial lake deposits, and it was connected to a source of high pressure water, probably historic high pressure water. And what happened was that the total flow from that was 250 litres per second, compared with a total flow of only 10 litres per second that was required to depressurise the whole of the excavation. So that was a nasty moment. It hadn't been on the model. It hadn't been picked up on the site investigation. It was reasonably straightforward to explain with the benefit of hindsight, but it did give one or two nasty moments. So we can see there the huge flow that came in. It flowed for about 4 weeks, but when it was gone, it was gone. And then it wasn't necessary to pump it anymore. Then the final slide, which we can just stay on there, but that shows the completed road, again, looking down into the tunnel. And I think that's the last one of the case studies, so I'll now hand back to Ian.
Thanks very much, William, and to Tim, Mark and Martin. And I'm sure you can now appreciate the breadth of knowledge and highly relevant content that is contained in the special publication, which will be available to purchase in early mid 2022. It has taken a long time to get to this point. One of our authors, Mike de Freitas, noted that it has taken a really long time to get to this point. In 1985, the engineering group attempted to gather hydrogeology and engineering geology together using a 5-day symposium, the proceedings of which formed the third special publication of the engineering group. And it's interesting to reflect that for one reason or another, it's taken another 36 years to pull the various threads together as a practical workmanlike document for use by industry practitioners. I think, and I hope you'll agree, that it was worth the wait. So now we've got some time for questions. If anyone's got any, please put them in the chat or raise your hand. Ursula, are there any questions that are already in the chat box?
There's no questions in the chat box, but several people have got their hands up. David Shuston's got his hand up. David, if you could unmute yourself and lower your hand, please.
Right, I'm here now. I just wanted to say what a wonderful report. Thank you ever so much, everybody. I'm really looking forward to spending a few bob and buying it in due course.
Excellent, thank you, David.
That's it for the moment. Has anybody else got any further questions?
Well, I'll say it's been fascinating working with all the authors. I have to say I've learned an awful lot from the experience, and I say I'm sure you will from the sponsors and the companies that you can see on the screen there. See that it's a real wealth of information and a wealth of knowledge that we've been mining to get to the bottom of this book. So hopefully any questions that you have either A, been answered, or B, you're just wanting to wait so you can see the publication for yourself. Actually, we've got one question there, I think, from Mark Edmondson. If you want to unmute yourself and ask the question, Mark.
Hi, Ian. It was just a comment that the meeting chat is actually muted. So you're not going to get verbal questions. However, alongside that, there was something that touched a nerve with me that Mark Lee brought up about communication. And it's a flavour of that presentation. It's about communication between geologists, hydrogeologists. Is there anything in this about guidance, about softer skills? Because we as a technical community, that we all recognise this problem. We have to communicate that to absolute non-technical specialists, to site managers, to contracts managers, and how, you know, those softer skills, how do we get better as an industry doing that?
Yeah, I think I can answer that, Mark. We've got sections in the publication about building the right teams, and that obviously includes teams from across the whole construction piece, from the sort of project managers through to the construction professionals and the designers. So I would say yes, we have gone some way to try and address that, but without telling people sort of how specifically to go about it. I don't know if any of the other authors want to add to that.
Well, it's Martin here. I was the co-author with Mark Lee on the Analytical Chapter, and I'm Mark, can correct me if I'm wrong, but I'm fairly sure there is actually a section at the back of the Analytical Models chapters on communication of results, where we discuss exactly that problem. I'm not convinced we have any answers, but we certainly highlight the fact that a model is of no value if it isn't communicated. The challenge is communicating it in the right form for the right audience.
Thanks, Martin. Thanks, Mark.
Thanks both, and I kind of fully agree. It's more a sort of preemptive. The flavour I got was very much about communicating internally as an industry, but actually the message needs to get out there.
Absolutely.
Contribute just to point out that a great deal of attention has been given to illustrations in this publication. It is a very heavily illustrated publication, and I'm sure the illustrations will assist many engineering geologists communicate with hydrologists and hydrogeologists and others in different fields, just as a cartoon does. So it's not just words. A great deal of time has been spent on getting this across in other forms of communication.
Thanks very much, Mike.
Thank you.
Got another question there from Mark Wheeler. Do the authors or presenters having produced an excellent report foresee a time when groundwater investigation has legal backing in much the same way as contaminated land investigation has? I wonder if Toby or William would like to answer that.
So if Toby's around, I would probably hand it off to him. But I do know these things are a very, very slow. So I do remember a particular case that we got involved with, Toby, where actually it was kind of almost criminal that they didn't have a groundwater investigation. But anyway, Toby, you've probably got something sensible to say.
Well, yes. Well, I don't foresee a time when we're going to have legal backing. That's for sure. Although it would be nice to have the force of law behind us when we turn up to investigate a site.
So with this particular case, it was very interesting because they totally ignored the tender for groundwater control. Eventually, and I remember Toby was so anxious that he said he actually sent them the quote by recorded delivery. And he phoned them up and said, "What do you think of our quote?" And they said, "Well, we've got a different way of doing it." "What's that?" "We'll dig and see what happens." And sure enough, the base of the excavation blew. So we did go down there and we helped them sort it out. And then unbelievably, they said, could we help them with their Clause 12 claim for unforeseen ground conditions?
Excellent stuff. Okay.
Did I briefly see a hand up from Claire Howarth?
Yeah, hi there, Ursula. I just wanted, as well as extending my personal thanks to your good self, Ursula and Ian, for championing, and it has been a championing cause from there. As a representative of the hydrogeological community and the hydrogeological group. And I know Mark Lee will also reiterate that as well with me. This piece of guidance has been needing to bring our disciplines together, and I've been promoting it across my hydrogeological community as to how to actually learn about engineering. So it's not just the engineering, geology and geotechnical industry that will benefit from this. I think the wider hydrogeological community as well. So I was just wanting to reiterate, and I will also underline that there's been a very deliberate choice of style to make this palatable, non-mathematical, and to start talking the same language. Because even after 20 years as a hydrogeology practitioner, it amazes me how often I'm not on the same page. So that was all I wanted to add to the component.
Thank you, Claire. Mike, have you got another question, or is that a relict hand?
I think it's a new hand, Christine.
I think we've got a new question from Jenny Cook as well.
Okay.
Jenny, do you want to ask your question directly?
Yes, I will. We know from the IPCC report and also the one by Dame Julia Slingo for Network Rail earlier this year that we are in an unusual time in terms of the amount of water that we can expect to fall is not easy to guess from historical records. So how have we taken that into account when we're looking at groundwater issues?
Who would be best to answer this? Could this be?
I'll just say a word, Ian. I mean, in terms of trying to recognise the scale and extent of groundwater problems that we face, we have a relatively light touch on that in terms of climate change and so on, and we just acknowledge that we don't know where it's going to go. There are various studies in hand at the moment, but we can just anticipate that if surface water problems and flooding and so on are going to get worse, then we can just imagine that groundwater problems are going to get worse. That isn't a help, it isn't an answer, but we do nod in that direction, saying we don't know everything that's going to be we're going to be facing in 25, 30 years time. That's for sure. I don't know whether anybody else has any thoughts.
Yeah, I think just one thing, sort of from my perspective, I think is key to actually addressing and effectively managing that change is going to be the application of the 3 different model types and making sure that we've got a properly joined up approach in terms of the engineering and the hydrogeology, and that we can work together as 2 very complementary communities to actually address that, because there is a huge amount of uncertainty, and it's a big consideration when you're looking at a new infrastructure or existing infrastructure in terms of climate resilience is how is this changing environment, changing climate going to impact on those natural processes and the stresses and strains that structures are put under that they either weren't designed to face because they weren't designed with climate change in mind, or they've been designed but not got the predictions right because we haven't as a species done what we need to do to get it back under control. So yeah, I think it's more about principles and how we can factor that in rather than sort of specifically addressing it, but hopefully it'll help with how we can play our part in managing that.
Thank you.
Vanessa, I was just going to say, I wondered if BGS had any sort of comment on that, or move Vanessa.
Thank you very much indeed, Ian. I think our perspective is trying to ensure that monitoring is as comprehensive as possible in terms of what we're bringing to our conceptual understanding. So making sure that we capture extremes in the data and understanding where we can, guiding people to take cognizance of guidance that is outside there as well. So signposting elsewhere to source the right information for that purpose.
Okay, thank you.
Somebody's posted in the chat, Miguel has said that the Geological Society Special Publication 288 covers the topic of climate change and groundwater.
Great. Right, I think we're probably about bang on time for finishing. So I don't, if there's one more question, we can take it. I don't think there are. Other than that, I'll just hand back to Ursula.
Cool. Thank you, Ian. I'd like to thank Ian, Tim, Mark, William, and the rest of the Groundwater Working Party for a fascinating presentation. Pretty much the entire Working Party has been in attendance, as you've seen, and we look forward to the publication of the special publication next year. Many thanks to all those who contributed with interesting questions. It's extended the topic quite well. It just remains for me to remind people that our next event is the Gloss-Up on the 24th of November at the Royal Institution, and then bid you all good night.